Let us now talk about delete in C++. It is strongly recommended to see the previous video where we introduced delete. Please remember there were three cases. The first case was when the node to be deleted is a leaf node. The second case was when the node to be deleted has only one child. The third case was when the node to be deleted has both children as non-empty. One thing in delete, like insert, to delete you need to search the key first, right? So this code, if you see, it's similar to the search function. Suppose I want to delete 60 here, so I'll begin from the root, I'll go to the right because 60 is greater than 50. So I'll come here, I'll see that 60 is smaller, so I'll come here and that's where I find the key. So this part of the code is similar to insert function. We have already talked about insert function, right? So if root is empty, we return the root because there's nothing to be deleted in an empty tree. If you want to delete something from an empty tree, you can't delete, right? Because there's nothing to delete it. If root arrow key is greater than x, then we go to the left child because the key that you are deleting must exist in the left side because key's root itself is greater. Otherwise, we go to the right child. This part of this code is similar to the insert function. And this part of the code is to handle the case when your root arrow key becomes equal to x. When you reach the node that you want to delete, what do you do then? For example, you want to delete 60, you will come into this else part when you reach this, when this is your root. And suppose you want to delete 70, you will come into this else part when this 70 is the node, right? When then 70 is the current root. So we begin our execution here. We suppose are deleting 60, we'll come here, then we'll come here, this is our current root. So we will come to the else part, and in the else part, we have written code to handle the three cases. The case when it is a leaf and it has one child and both the children are non-empty. So this case handles, this if condition handles when the left child is empty. It means right child can either be empty or non-empty. So what we do is, we find the right child, we return the right child as a new root of the subtree where this node is present. And then we delete this node. What do we mean by return this right child as the subtree? Suppose you were deleting, suppose this is not there and you were deleting 30, right? So you'll come to this if part. And what will you do? You will make temp equal to root arrow right. Then you will delete root. This is your root. You will delete here. After deleting the root, you will return temp. You will return temp to the parent caller. For this 30, the parent caller was 50. So this comes here in this call because your parent must have called for the left subtree and this is how they are attached. So 40 becomes the left child of your parent. This is how they become linked and this is gone out of the picture and you wanted to delete 30, right? That's how deletion happens when one child is empty. And the same logic is for the right child. If right child is empty, you have similar logic as you have for the left child. This if condition also handles the case when both the children are empty. Suppose you want to delete 40, right? So you will start traversing from here, then you will come here, then you will come here. And you will see that 40 is matching the key that you want to delete, so you will come into the else part. And then you will see root arrow left is null. So you will come inside this if part and your temp will become root arrow right, which is null. So your temp will become null. And what will you do now? You will delete 40 and you will return temp, which means you are going to return null to the parent. And what parent is going to do? Parent is going to make root arrow right equal to null. So the parent's right is going to become ultimately null. And that's what you want. The 40 is deleted and it has no right child now. Null means no right child. So we have understood all the cases. Only case left now is when both the children are non-empty. To understand the case, let's take this example. Let's say we want to delete 50. So what we do when we delete a node which has both the children as non-empty, we find the in-order successor, closest greater value, which is 55 here. And our output is going to be 55 is going to come here and this node is going to out of the tree, right? That's what we want as a result. Now, when both the children are non-empty, we are going to come into this else part, right? Because left is not null, right is not null. And what do we do in the else part? We find the successor of the current node. So root is here because this is where you come when matches with the given key. You want to delete 50 and your root is here. So you find the successor. How do you find the successor? How do you find the closest greater value? The closest greater value is leftmost leaf of the right child. Leftmost leaf of the right child. So this is the right child and the leftmost leaf in this right child is 55. So you simply go to the right child, 70, then you start traversing, you go left, 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 right? You're simply going current equal to current arrow left in a loop, and the leftmost is the node where you stop and you return this as a successor. So you get the successor as this node. And what do you do after getting the successor? You copy this value 55 here. You copy 55 here, right? And now you recursively call delete for this 55 in this particular subtree, right? You recursively call the same function, which is going to delete 55. And when you recursively call for deleting this 55, this will go into this particular case because it's a leaf node. When root is here, root arrow left will become null and you will delete 55 by doing normal deletion. So we have talked about delete implementation in C++. We have talked about 3 cases. One interesting thing I would like to share about the delete operation. When you are deleting a node and in the delete, when you find in order successor, it works. But we can't use this get successor function in general to get in order successor of a node. This in order successor function gives you successor only when your right child is empty. In general, for any arbitrary node, if you want to find the in order successor, your code would be slightly more complex than this one. And in BST delete, we need successor only when right child is not empty, right? Otherwise, we'll go into one of these cases. Let's see why. If you see the in order successor of 40, it's not there in the right child. Who is in order successor of 40? What is the closest value which is greater than 40? It's 50. It's not there in the right subtree because right subtree is empty. So in some cases, your successor may be one of the ancestors. So this get successor function does not give you general in order successor, but it gives you in order successor only when right child is not empty. Now let's talk about the time complexity of this solution. This solution works like search and insert. It's going to traverse the BST across the height. It's going to find the key, then it's going to delete the key. So the time complexity of the solution is big O of h. And since it is a recursive code, it's going to have big O of h extra space.